Namaskar. Very warm welcome to all the viewers and learners in this live interaction of CIT and CRT. I am Renu Bhatt with you all, and you are watching us live on eVidya channel number 12. And apart from this channel, you are with us on our YouTube channel as well, that is NCERT official and PMeVIDYA class number 12. मैं हूं रेणु भट्ट, आप सभी के साथ आप सभी का स्वागत करती हूं अपने इस लाइव इंटरेक्शन में। अपने सभी देखने वालों को हम बता दें कि हम इस सत्र पे किस विषय में बात करने वाले हैं। हम इस सत्र में मैथमेटिक्स के 12th स्टैंडर्ड के स्टूडेंट्स के लिए बात करेंगे और हमारा टॉपिक रहने वाला है लीनियर प्रोग्रामिंग पार्ट 1। तो इस टॉपिक पे बात करेंगे एंड यू मस्ट बी वंडरिंग about the content. Definitely we have joined by our expert to throw more light on this particular topic. It's an optimizing technique, dear learners and viewers, and in case आप इस चैप्टर में कहीं पर अटक गए हैं या आपको इसके बारे में ज़्यादा जानना चाहते हैं तो आप हमसे हमारे विभिन्न माध्यमों से जुड़ सकते हैं। आप हमें कॉल कर सकते हैं हमारे टेलीफोन नंबर पर जो है 8800440559। Either you can drop a mail as well. हमारा email address है dth.class12@cit.nic.in। अगर आप हमारे YouTube चैनल्स पर हैं यानी कि NCERT ऑफिशियल PMeVIDYA क्लास नंबर 12 पर हैं तो आप लाइव चैट बॉक्स में जाके अपना कमेंट ड्रॉप कर सकते हैं। ये सबसे तेज़ माध्यम है हमसे जुड़ने का और हम चाहते हैं कि ज़्यादा से ज़्यादा अपनी क्वेरीज़ के साथ आप हमसे हमारे इस लाइव इंटरेक्शन में जुड़ें। तो हम अपने सभी देखने वालों को बता दें कि हमारे साथ हमारे एक्सपर्ट जुड़ चुके हैं। तो चलिए अब हम उनसे परिचय लेते हैं। आप हैं श्री राहुल सोफाट सर, आपका बहुत बहुत स्वागत है।
हेलो मैम।
और हम बता दें अपने सभी देखने वालों को कि सर इज़ HOD हेड ऑफ डिपार्टमेंट ऑफ मैथमेटिक्स फ्रॉम एयरफोर्स गोल्डन जुबली इंस्टीट्यूट न्यू दिल्ली। एक बार फिर से मैं आप सभी को बता दूं हमारे वो तरीके जिनके माध्यम से आप हमसे जुड़ सकते हैं। वी आर वेटिंग फॉर योर पार्टिसिपेशन इन दिस पर्टिकुलर लाइव इंटरेक्शन विद ऑल योर क्वेरीज एंड डाउट्स। आप हमें कॉल कीजिए हमारे टेलीफोन नंबर पर जो है 8800040559 एंड आप हमें मेल कीजिए अपने फीडबैक के साथ भी कि आपको हमारे सारे लाइव इंटरेक्शन कैसे लगते हैं ऑन dth.class12@cit.nic.in। सो जब तक आप हमसे जुड़ते हैं हम अपना लाइव इंटरेक्शन यानी कि आज का डिस्कशन शुरू करते हैं ऑन लीनियर प्रोग्रामिंग पार्ट फर्स्ट। तो सर हम आपके पास आएंगे एंड वी वुड रिक्वेस्ट यू टू टेल अस अबाउट द लीनियर प्रोग्रामिंग एंड व्हाट एल्स यू आर हैविंग इन दिस पर्टिकुलर सेशन मैम। सर
Today, dear learners, we'll be doing a very important topic for class 12th, which is linear programming. And what is linear programming? Linear programming is an optimization technique. Optimization means if we have to maximize or minimize, then this technique is used. But the important thing which you must know is that in linear programming, our objective function followed by the constraints or restrictions which we are having are linear in nature. They cannot be quadratic. So that is the only condition. And as you will learn this topic, you will realize how important and how interesting it is. And it has got many applications in real life problems.
ओके तो हम शुरू करते हैं अपना आज का सेशन। जी सर।
Yeah. So starting with linear programming, first thing is it has, as I just told you, it has many applications in mathematics, and this is one of the important concepts which is there, and it is used for many application and real life problems, and it involves system of inequalities or equations. So in this session we shall apply the system of linear inequalities and equations to solve these problems. Now how you will define an LPP? So linear programming problem is one that is concerned with finding the optimal value. So optimal value means either maximum value or minimum value, that is maximum or minimum of a linear function called objective function of several variables. You can have more than 2 variables also, but in our curriculum we will restrict ourselves to only 2 variables x and y, subject to the condition that the variables are non-negative. See, most of the times in real life we see the variables takes non-negative values, they are positive and satisfy a set of linear inequalities called linear constraints. So the basic structure of linear programming is the main basic thing which you must know is what is linear programming. It is an method to find the maximum or minimum value of a linear function which is called the objective function under certain restrictions which are there. So, those restrictions have to be satisfied. So, next we will move ahead. Some important terms used in LPP, right? Objective function, linear function z equal to ax plus by, where a and b are constants, they are all, these are real constants a and b, which have to be maximized or minimized, is called the linear objective function. So, whenever you will see a linear programming problem, the first thing you must know is what is the objective. Objective means what is the purpose, what is the aim. So, that is the objective function. Our objective function can be to maximize the profit of a company which is producing 2 items or more than 2 items, but here we will be taking 2 items, how much they should produce so that their profit is maximized. It can be to minimize the cost, so it can be to maximize the revenue. So, that is objective function. A and B are constants, and these A and B are called decision variables, and our aim can be either to maximize or minimize. For example, P equal to 30x plus 40y, and our aim is to maximize the profit. Here x and y can be the number of you can say units which a company should produce to maximize the profit, and on one unit of let us say a company is manufacturing 2 products, ball pen and a sharpener. So, on one ball pen the profit is rupees 30 for 1 unit, and one sharpener the profit is 40 rupees per unit. So, what is the total production x and y, how much of each the company should produce so that our combined profit is maximum. So, this type of function which is linear in nature gives us the objective function, right. So, and x and y, as I have told you, are called decision variables because we have to decide how much of each is to be produced so that our profit is maximum. Now, next comes constraints. Now, what are constraints? I have now given an example of a linear programming problem. The linear inequalities or equations or restrictions on the variables of a linear programming problem are called constraints. See, as I have just told you, this maximize z equal to 1000x plus 1200y, right. This is the objective function. Now, here it can be like actually in all these problems we have to find how much x and y, what values of x and y should be there. Our aim is to find x and y which will maximize this z. So, that is the aim. This is our objective, hence it is known as objective function. Subject to the constraints, we are see, the resources are not infinite. So, whenever we have certain resources which are finite, we have certain restrictions. So, those restrictions are in the form of the constraints, that 8x plus 11y cannot be greater than 450. So, this value should always be less than or equal to 450 for this particular problem, and 2x plus 3y should be less than or equal to 100. This is the second constraint, and we are considering x and y should take non-negative values, because suppose you are producing certain units, we cannot produce negative units. Therefore, most of the times in our linear programming problem, these non-negative restrictions are there, that the variables x and y, which are our decision variables, have to take only positive values, or they can be 0, but they cannot be negative. So, this is also given in our problem, or when you are formulating, then you have to write these on the basis of the question which is there, where you can get a hint that x and y cannot be negative. So, in this problem you will find there are 4 constraints. These are 4 constraints, and we have to find values of x and y which satisfies all these 4 constraints, all these 4, and then the values of x and y that particular point which maximizes the value of z. So, this is the objective function, maximum z equal to 1000x plus 1200y, followed by these 4 constraints. These is the first constraint, 8x plus 11y is less than 450. Second constraint is 2x plus 3y less than or equal to 100, and third and fourth are known as non-negativity conditions or non-negative restrictions, that our value has to be greater than or equal to 0. So, this is the format of our linear LPP, linear programming problem, and these 4 are the constraints which are following our objective. Now, next is, what do you mean by an optimization problem? A problem which maximizes or minimizes a linear function, like in the previous slide we have seen, we have to maximize an objective function which is linear subject to certain constraints. Constraints were again linear, they were linear inequalities as determined by the set of linear inequalities is called an optimization problem. So, we can have other optimization problems also based on the other concepts, but in linear programming problem is an optimization problem because we generally either maximize or minimize the value of z. LPP are special type of optimization problems.
So, here I would like to ask a question, and as you are telling us about optimization problems, we want to know about the difference between maxima, minima and LPP, sir, as both are optimization problems, sir.
See, maxima minima is in our differentiation, that comes under application of calculus. That is also an optimization problem, but the difference between maxima minima and this linear programming problem are, besides being both optimization problem, they are based on different concepts. Like maxima minima, we use calculus, we differentiate and equate it equal to 0 to optimize, and in linear programming problem we are working under different set of conditions. There are restrictions which are given to us, and at the same time all our inequalities are linear inequalities. As well, they can be equations also, but they are linear. So, therefore, both are optimization problem, but we say linear programming problem are special type of optimization problem.
Okay.
I hope it is clear to the students.
Yes, sir.
Now, see, our linear programming problem, there are different methods to solve the problem. One of them is the graphical method, which is there in our syllabus. So, students, we have to study only the graphical method to solve the linear programming problem. There are other algebraic methods also in which we do calculation, but we do not draw the graph by simplex method, that is known as. But right now we will be confining ourselves to the graphical method. Now, first of all, let us recall how to find the solution of the linear inequality involving two variables x and y graphically. So, this we have done earlier, but this is the important basic of our solving the linear programming problem graphically. So, what we will do is, we will consider this inequality 2x plus 3y less than equal to 12. Now, we will learn how to draw its graph and what it represents. Now, if you look at this inequality 2x plus 3y less than equal to 12, we can say it constitutes of two parts. One is 2x plus 3y equal to 12. See, when less than equal to is there, all of you know it is equivalent to all the points which satisfy this equation, because I am taking equality first, 2x plus 3y equal to 12, and then I am taking this strict inequality 2x plus 3y less than equal to 12. So, if you can think of this inequality 2x plus 3y less than equal to 12 as 2x plus 3y equal to 12 and 2x plus 3y less than 12, you combine these two, this or this, both of them satisfies this inequality. So, the equality 1 is a straight line. So, this is a straight line 2x plus 3y equal to 12. When the equation is there, when the equality is there, it is all the points on the straight line that will satisfy this equality. And the second part 2x plus 3y less than 12 is, this is a strict inequality. It represents a region below the line. So, whatever region lies below the line, that will be satisfied by this inequality. And how you will know that all the points below the line will be satisfied by this inequality, or all points below the line will satisfy this inequality? Because we have to substitute the coordinates of a particular point which is below the line. Now, here the best point to take is origin. If you put 0 0 in place of x and y, you will realize that this will give you 0 plus 0 which is again 0, and 0 is less than 12. So, we will shade towards the origin, and towards the origin means all points below the line, below this line towards the origin will satisfy this strict inequality. So, I hope students, this is clear to you, that when you are graphically trying to find out the solution of the strict inequality, it has two components. One is all the points on the line 2x plus 3y equal to 12, and the second is all the points in the region which lies below the line. So, if you combine these two, we can say that all points on the line and all points below the line will be the solution, or will be the solution set of this inequality. And at times it can be the other way around also. It can be the points above the line can also be the solution if this inequality is the other way around, if it is greater than equal to. So, we will learn it later, and this is a simple and the most important concept which is used to solve all linear programming problems graphically. Now, see, if we draw this line 2x plus 3y equal to 12, you can draw a table, take values of x and y, first assume some value of x, find the corresponding value of y and plot it on the graph. You will get when x is 10, you will get y is 0, right, and then you take some point here also 0, 5 and draw this line, right. So, it involves two variables x and y. So, and this is the straight line, this is a straight line, and all points below this line are the region 2x plus 3y less than 12. So, what you have to remember is the line will be a linear straight line, and all points below it will be the region. It is actually the open half plane, and this below this line, right, half plane either below or above depending upon the inequality. Now, next is let us find the feasible region of the following two constraints. See, in linear programming problem you can have more than one constraint, two constraints, three constraints, four constraints. So, how to go about it? Now, here we have 3x plus 4y less than equal to 60, x plus 3y less than equal to 30, and at the same time we are taking x and y, this non-negative restrictions or non-negativity condition is also there, x and y both are positive. So, these are trivial in nature, but these two constraints we have to draw, and x and y greater than equal to 0 basically means that we have to restrict ourselves to the first quadrant. So, see how we can draw the graph here. These are the graphs. If you look at the two lines which we have drawn, right. So, yeah, I will go back to the previous slide. Yeah, see the first constraint 3x plus 4y is less than equal to 60. So, here if you see what are the points where it intersects the axes, x axis will be intersected at 20 and y axis will be intersected at 15. So, first line is 15, 20. So, if I look into it, yeah, this is 15, 20, this is a point 15 and this is 20, this is the first line, first constraint, and where I am shading towards the origin because it is less than, type, therefore, our what you call shading will be towards the origin, it is less than 60. Now, if you take the second constraint x plus 3y less than equal to 30, here you will find if this, when you will put y equal to 0, x will be 30, and when you will put x equal to 0, y will be 10. So, this again if you put 0, 0 to find out which direction I have to shade, I will get 0 is less than equal to 30, that means origin, I have to shade towards the origin, right. So, see, this is the second line, and again our shading is towards the origin. Now, when both the shades are towards the origin, we have to find the common shade, the common region where both the shades are coming. So, here this part, if you see this part, only this constraint is being satisfied, and if you take this part which is green in color, you will observe only this constraint is satisfied, this second constraint. But if you look at this purple color, this is the common region, that means here both the constraints are being satisfied, because in this purple region all the points below this line will also be there, and all the points below this line is also there. So, what we see is what we observe is this is known as the feasible region. feasible region in case of two constraints is that region which every point in it will satisfy both the constraints. This is not feasible region because only one of the constraints is satisfying its inequality, and this is also not feasible because all points here will are not satisfying both the constraints. But this purple region, this region O, A, B, C is known as the you can say common feasible region or feasible region, because here both the constraints are being satisfied. Now, what is feasible region? Now, we have the formal definition of feasible region, the common region determined by all the constraints including the non-negative constraints. See, you have to, this non-negative constraints are equally important, because if you are considering it, that is the only reason we are restricting ourselves to the first quadrant. See, this is positive x axis, this is positive y axis. So, we are not going beyond the first quadrant because x and y are greater than equal to 0. So, the region where all the constraints are satisfied, the two constraints which we took, those two constraints, see these two constraints as well as these two non-negativity constraint also. So, all the constraints are being satisfied, that is the feasible region. So, here OABC, every point in this region OABC, not only inside this, but all points on this boundary will satisfy our all the four constraints. Therefore, this is known as the feasible region, or we can say solution set of the given constraints. Now, next, graphical method of solving the linear programming problem. Now, we will solve one problem graphically and we will find out the solution. Now, here the difference is, besides those constraints, we have also taken the objective function. Let us say that the objective function is maximum z is equal to 8000 x plus 12,000 y. This is our objective function. We have to maximize the value of z, and whatever our restrictions or constraints, this we have taken earlier also, 3x plus 4y less than equal to 60, x plus 3y less than equal to 30, these are our two constraints, x and y are greater than equal to 0. Now, see, when we have drawn these two constraints, this is the same graph which we have drawn earlier in our earlier feasible region. So, it remains the same. What we will do is, we will find the corner points. This is the feasible region. Now, we have to take the corner points of the feasible region. This is the point O, this is the point A, this is the point B, and finally, this is the point C. So, corner points or vertices we will write here, see O, origin A, this is A 0 10, and then we will take the point B 12 6, and then we will take the point C 20 0. Now, and our aim is to maximize the value of z, which was 8000 x plus 12,000 y. Now, if I substitute, if I am not producing anything, if value of x and y are 0, our value of z will also be 0. If the point is 0 10, in place of x I will write 0 and in place of y I will write 10. So, this will give us 1,20,000. Now, if I take the next point 12 6, substitute values of x and y in this objective function, this is our objective function, then I get value of z as 1,68,000, and finally, when I put 20 0, our last point, see these are the corner points O, A, B, C, this point C is 20 0, when I put 20 0 here, I will get 1,60,000. Now, if you compare all these, now you have this table in front of you, and you can see which value is maximum. Now, 1,68,000 is greater than all other values. So, we conclude that the maximum value of z is 1,68,000, and it is attained when x takes the value 12 and y takes the value 6. So, the maximum value is 1,68,000, and at what point it is taking the maximum value, that is 12 6 at the point B, this 12 6. So, when x is 12 units and y is 6 units, then our objective function will attain its maximum value, and the maximum value is also here 1,68,000. So, it is like just by comparison, we will find out this value of z at all the corner points, and then we will compare this table and see whatever we want to do. If we have to find the maximum value, then this is the maximum value, and if you have to find the minimum value, that also you can easily find by looking at it. But here our objective was to maximize. So, we are not looking at minima, see maximum z. I hope this is clear to our students. And
Sir, here I want to know, can we have no solution in an LPP, sir?
yeah, we can have no solution in our LPP, and in that case there is no region which satisfies both the constraints. One shading is away from the origin and the other shading is towards the origin, and the two lines are not intersecting. Then in that case we will have no solution.
Okay.
I will explain you with the help of a model how no solution is formed. I will just consider it. See, this is our linear programming kit. See, now suppose there is a constraint x plus y is equal to 60 or x plus y equal to 100, you can take any constraint you can take, x plus y is equal to 100. So, it will intersect, or for that matter I am taking 80 because 80 or 80 any value. So, if I am taking x plus y is less than equal to 80, then our shade will be towards the origin. See, the shading will be in this direction towards the origin.
Okay.
So, this is the line, this string is representing the line x plus y equal to 80. We are also considering that x plus y is less than equal to 80, at the same time x and y are both positive. So, our region which will be there will be in the first quadrant. So, every point on this line, and these are the arrow marks, and all points below the line will be satisfying this constraint, right. Now, if I consider if I want to represent or if I want to show the solution of the inequality x plus y is greater than 80, then the only thing is it will intersect both x and y at 80, and then our shading will be away from the origin, x plus y is greater than 80. So, this is the region. Now, if I take another constraint, let me take another constraint. See, I will just, this is x plus y less than equal to 80, and the shading here is in the other direction. If I am taking 100 and 110 here or 120 here, now you see, will there be any common region? One shading is away from the origin, the shade of this, and the shade of this line which was cutting the x and y axis at 80 each, the shade of this is below the origin. So, when one shade is going away from the origin and the shade of this first, the inner line is below, then is there any region where both the shades will come? So, nowhere both the shades will be coming. So, this is the case when no solution will be there. Okay. We can just show it on the, I will draw and show it to you. Like these are the axes, this is x axis, this is y axis. Now, if I take a constraint like this, its shading is towards the origin because it will be like this sort of inequality, right. And then the other constraint is like this. So, this is the case of no solution. Okay. Here there is no region where both the shades will come. So, we can have a no solution type of a thing. Now, again we will continue with our topic, graphical method of solving linear programming problem. So, here maximum z is equal to 600 plus 200y subject to these three constraints, and besides this we have these two non-negativity condition or non-negative restriction also. These are actually, all of them are constraints, but whenever x and y are greater than equal to 0 is given, we know that its result will be restriction, that we will restrict ourselves to the first quadrant. So, we just take that into our solution, right. So, let us move ahead. See, so here what we have done is I am drawing all the constraints one by one. First is x plus 2y is less than equal to 12. This constraint, or first you draw the equation. It will cut y axis at 6 and x axis at 12. So, see, y axis at 6 and this will cut x axis at 12 if you move further ahead, right. This is our first constraint, this one, and our shading is towards the origin. So, the shading will be like this, right. And now you see the second constraint, 2x plus y is less than equal to 12. This will cut y axis at 12 and x axis at 6. So, y axis at 12 and x axis at 6, this is the constraint, x axis at 6 and y axis is 12. See, you can always try to choose the scale in such a manner, so that even the points of intersection with the axis are also shown in the graph. Here I have enlarged this so that these points are clear to you. Otherwise, the scale should be taken in a manner, so not only the point of intersection, the corner points, but besides that the point of intersection with the axis, if that are also clearly visible, so that will be better, right. Now, the third constraint is this one, x plus 5 by 4 y less than equal to 5. See, here I think in your earlier classes you have done how to draw these straight lines. First you will just take equality into consideration. अभी inequality को सबको equality में consider करेंगे and will draw straight lines, and after drawing the straight line, putting the origin or some other value of any point which is not on the line and substituting here, if it satisfies this inequality, then we will shade towards the point, and if it does not satisfy this inequality, then we will shade away from that point. So, first you convert all of them into equal to, draw the straight lines, and that too you can draw a table and take different values of x and y, and 2 points are sufficient to draw a straight line, but you can take 3 points in case of like you can all like if you take the third point, it verifies that everything is correct, right. Then you shade them. The last constraint will be cutting x axis at 5 and y axis at 4. See, x axis at 5 and y axis at 4, this is the third constraint. But you see the direction of the inequality, here the inequality is not less than, it is greater than. So, our shading is away from the origin, greater than a. So, this shade is greater than, right, this shade is below, right, and this shade is also below. So, what will happen if you take the cumulative or the combined effect of all the 3 constraints? You will observe that this region is the one in which all the 3 constraints are satisfied. Here it is triple shaded, it is the shade of this constraint is also coming, the shade of this constraint is also coming, and the shade of this constraint which is moving upward will also come. So, this is known as the feasible region in this case, and these are the corner points of feasible region, A which is 0 4, B which is 0 6, C which is 4 4, D 6 0, and this is E which is 5 0. So, these are the corner points, and there is a very important theorem which states why we are taking the corner point as the possible points where we can find the optimal solution, and in our next slides you will see that theorem is also there, and because of which we are just checking at the corner points, right. So, if we move ahead at all these corner points, I will find value of z. Z is 600 plus 200y. The corner points are A 0 4, B 0 6, C 4 4, D 6 0, and finally E 5 0, right. These I make a table tabular form में, I will take the corner points and I will write their coordinates, then I will substitute in the objective function which is 600x plus 200y. Now, it is very simple, just substitute the value of x and y in this objective function. You will get this is 800, then next you will get, if you put 6 here, this is 1200, you put 4 4 in place of x and y, and then you will get 3200, and if you put 6 0 you will get 3600, and finally if you put 5 0 you get 3000, 5 into 600 is 3000. Now, you just compare by inspection, you can find out which is the maximum value. I have to find the maximum value of z, and 3600 is greater than 3000 also, 3200 also, and these two values also. So, what we conclude? Finally, you have to write the answer. What you will write? Maximum value of z is 3600 at the point D which is 60, or you can write maximum value of z is 3600 at x equal to 6 and y equal to 0. So, this is how you will solve these problems, and will further now see why we are taking all the corner points, and this is done because of this theorem. This is a very important theorem, right, and because of this I first tried to solve one or two problems so that you can understand the problem easily, understand the theorem easily. Now you know what we did. First, the objective function and the constraints were there. Graphically we have drawn the constraints. First the linear part, the straight line, then we have shaded the inequality part just to know whether it is the lower half plane or the upper half plane, right. See, if you include the line, it is half plane. If you do not include the line, it is the region represented by the strict inequality, which is open half plane, right. So, then after drawing all the constraints and their shades, we are finding the feasible region. Feasible region is which region? Where all the shades are satisfied, all the constraints are satisfied. Then we are taking the corner points. Then we are finding the value of the objective function at corner points, and then we are finding the maximum or minimum value as the case may be. Now comes this theorem. Now the theorem states, let R be the feasible region, a convex polygon. This is also important, that the feasible region should be convex, like all triangles are convex. Convex region means like this, there is no indent, right, that is not convex. So, let R be the feasible region which is convex polygon for an linear programming problem, and let Z is equal to Ax plus By, it is the objective function. When Z has optimal value where x and y are subject to constraints described by the linear inequalities, this optimal value must occur at the corner point vertex of the feasible region. So, this theorem states that if the feasible region is there, right, and that is convex in nature, and Z equal to Ax plus By is the objective function, then Z will have the optimum value only at the corner points of the feasible region. So, this is the theorem. Because of this theorem, we are just checking the value of Z only at the corner points or vertices of the feasible region, right. I hope this is clear to all the students. This is an important theorem because of which we are using the methodology to which we are doing to find out the optimal value. So, if Z has optimal value, it will occur only at the corner points. Now, next is another theorem comes here. This is, let R be the feasible region for a linear programming problem, and Z equal to Ax plus By is our objective function. If R is bounded, then the objective function Z has both maxima and minima. It has both a maximum value and minimum value of R, and each of these occur at the corner point of the feasible region. So, basically what is this theorem? Let there is some region, R is a feasible region, and this feasible region is bounded. Bounded means that region can be put inside a circle. Bounded means you can have a circle enclosing that region. So, if there is a feasible region which is bounded, means which can be there inside a circle, which can be enclosed inside a circle, then this objective function Z will have both maximum and minimum value. Then we will have a maximum value of Z as well as a minimum value of Z, that is bound to be there, that will be there, right, and these values will occur at the corner point or the vertex of the feasible region. So, what is the difference between this first theorem and this theorem? First theorem says that the optimal value will occur at the corner point. This theorem says that if the feasible region is there and this feasible region is bounded, then the optimal solution will always exist, but it will exist at the corner points. That this part of the theorem is taken from the first theorem itself, that the optimal value will occur at the vertex, but it will always occur. It is because of this concept that our feasible region is bounded. So, these were the two important theorems which because of which our taking the corner points and then finding the solution was done. Now, we will take this formal, I will define it, this corner point method. This is the method of solving the linear programming problem. This method comprises of the following steps. First is find the feasible region of the linear programming problem and determine its corner points, which is the vertices. Now, why I have taken this here? Because now you know what it means. Feasible region also you know. So, you can find the feasible region of the linear programming problem. This LPP means linear programming problem, and determine its corner points, all the vertices. Now, next is evaluate the objective function at each corner point. Find the value of z or the objective function at all the corner points, and let capital M and small m respectively denote the largest and the smallest value at these points. See, when we took the corner points in that tabular form and then we found the value of the objective function, और फिर हमने compare किया था the value which is maximum and the value which is minimum, right? So, let m and m be the largest and the smallest value at the some corner points, right? When the feasible region is bounded, then the largest value is the maximum value. See, sometimes it is not that the largest value and the lowest smallest value will give you the optimal value. It is only when the feasible region is bounded. So, this result is important. When the feasible region is bounded, then the largest value m is our maximum value, and the smallest value or the lowest value small m. One is capital M, which is the largest and it is the maximum value, and small m, if it is the smallest value, it will be the minimum value. So, it is only when the region is bounded. Now, here I want to just give you an important remark. If it is not bounded, if the feasible region is not bounded, that means it is unbounded, then the maximum or minimum value may or may not exist. The largest may not be the maximum value, right, or the smallest may not be the minimum value. Only if it is bounded, then the largest and the smallest gives us the maximum and minimum value. I hope this corner point method is very simple. You just find the common feasible region, you find the corner points. After finding the corner points, you find the value of the objective function z, and then generally we just compare. जो सबसे highest value है और the largest value है उसको हम maxima लिख देते हैं, और जो सबसे smallest value है उसको हम minima लिख देते हैं. But underlying this fact, you must remember, क्योंकि the feasible region is bounded, then only we can take these values as maxima and minima. Now, next is another problem. Solve the following LPP graphically. The problem is the objective function is maximize z equal to 2x plus y, subject to the constraints 3x plus 4y is less than equal to 1080. This is our first constraint. 3x plus 8y is less than equal to 1920. This is our second constraint, and x is less than equal to 200 is our third constraint. And x and non-negativity constraints or non-negativity condition is also there. Both x and y are positive. Now, see again, what I have done is, here I have tried to show each of the constraints separately. This first constraint, if you look, is the first one, right? 3x plus 4y is less than equal to 1080. This is the first constraint. This is the first constraint, this one. Then I am taking the second constraint. I have to flip back. 3x plus 8y is 1920 is our second constraint. So, I have taken the second constraint here. This is the second constraint, right? So, now the common region is this. This is the common region where both the constraints are satisfied, because in both the constraints the shading is towards the origin. So, when you are shading this towards the origin, both of them you are shading towards the origin. तो इधर का जो shade है, this is only satisfied by this constraint, this one, upper this constraint. The reason is because इसका shade तो नीचे आ रहा है इधर से, तो इधर तो एक single shade है, but ये shade इधर तक it will go towards the origin. तो जो इस line के नीचे जो region है, that is common. इधर का इस constraint का भी shade आएगा और इसका भी shade आएगा. Similarly, this triangle, small little triangle which you are having, इधर एक ही shade आ रहा है, only that green shade. But below this line, this green shade will also enter, and the shade below this constraint will also enter. So, this region, if you see the cursor or this arrow, this is common region to both the constraint. Then I am taking finally the third constraint. ये जो third constraint है, x is less than 200. You know, x is less than 200 is a line parallel to y axis, and it will cut ये देखो parallel to y axis, and it will cut x axis at 200. So this is our last constraint. So when this this constraint is drawn somewhere here, this is our 200. So ये इधर ये constraint हमने draw की है blue. ये जो third constraint है, this constraint actually it is drawn here. It is drawn here. ये ऐसे यहाँ से हमारा ये vertically line draw हो रहा है. And this is I have enlarged and shown this here. This is the third constraint. Now you see the common region. अब common region ऐसे आएगा, फिर इधर आएगा, then it will be here, और उसके बाद ये 200 के लिए एक ऐसे लाइन आएगी, vertical line. So this is a vertical line. इसी को हमने third constraint draw करने के बाद 200 पर, ऐसे 200 पर draw करने के बाद इसको enlarge कर दिया है, so that our students can see the corner points easily. So this is the corner point O, which is origin. This is the corner point A, 0, 240. This is the corner point B, 80, 210. And this is the corner point 200, 200C. And finally, we have this corner point D, 200, 0. After finding all these corner points, now you know the reason for taking only the coordinate point. Because it is bounded, the maxima minima both will exist. But here I think they have just asked maxima. So the maximum value will exist, but it will exist only at the corner points because it is bounded, right? Now we will move ahead. Solve the following LPP graphically. So, but before I, in the previous question you can solve it. Find the, here what we have done is, you can take these values A, B, C, D and then find the value of Z, and then you can see the maximum value is, whichever is the maximum, largest value will be the maximum value, right. Now, before I move further ahead, I will show you one more kit. This is developed at NCERT Educational Kit Department. See this constraint. I hope it is clear. We have this constraint x plus 2y is less than equal to 12. X plus 2y is less than equal to 12. Now it will cut x axis at 12. See, it is cutting x axis at 12.
सर थोड़ा इसे आपको उठाना पड़ेगा,
हाँ, so I think there is some
slightly tilt करना पड़ेगा, yes sir, so that we can see it properly.
Yeah, I think
yes sir,
now
that,
it is all
yes
right.
sir, that.
I'll just hold it this way. So x plus 2y is less than equal to 12, right? So this is the straight line, x plus 2y is equal to 12. It is cutting x axis at 12 and it will cut y axis at 6. So this is the straight line, and all the points below this, all the points below this will be satisfied because x and y are given to us as positive. Here it is mentioned x and y are positive, and this is x plus 2y is less than equal to 12. So all points below this towards the origin will be satisfying this constraint. Now this is the first constraint. Now I am taking another constraint. Now see this second constraint, x plus y is equal to 8. This is x plus y equal to 8. It is cutting x axis at 8 and it is cutting y axis at 8. It is cutting both x and y axis at 8. This is our second constraint, x plus y is less than equal to 8. This I have shown by this red what you call lines. तो ये जो region है पूरा हमने arrow से भी we can show, or we can draw these red lines starting from the line towards the origin. And why I am not going beyond x axis and y axis? Because x and y are both given to us as positive, right? This is our second constraint. Now when I will take both the constraints together, when I will take both these constraints together, see what will happen. First and second constraint, I'll just इसको
सर यहाँ पर मैं आपको बता दूं कि हमारे पास तकरीबन 4 मिनट का समय और शेष है सर. वी हैव लेफ्ट विद 4 more minutes सर.
Yeah. See, here this actually these are transparencies and different constraints are drawn on different transparencies. And when you keep them one below the other, it is, you can see how both the shades, This was what I was trying to explain you. Now here if you see, the first constraint was here, और उसका जो हमने शेडिंग था वो फर्स्ट कंस्ट्रेंट का ग्रीन पेन से किया था, एंड द सेकंड कंस्ट्रेंट इज, आई थिंक नाउ इट इज विजिबल, सेकंड कंस्ट्रेंट इज दिस सेकंड कंस्ट्रेंट, और इसका हमने शेडिंग रेड से किया है. नाउ यू विल ऑब्जर्व दैट here only the green shade is coming, in this only the green shade is coming, here only the red shade is coming, and here in this part both the shades are coming. So both the shades are coming from O, this is A, right, this is A, this is B, and this is our C, right. So both the shades are coming like this in this region. Now I will take the third constraint. This is our third constraint. I will first show you the third constraint. This is the third constraint, x is equal to 5. This is the third constraint. So x equal to 5 is a, you know, x equal to 5 is a straight line parallel to y axis cutting x axis at 5. Now here actually first I will always take the equality and draw, but the constraint was x is less than equal to 5. When x is less than equal to 5 is taken, then what happens? If you put 0, 0, 0 is less than 5, so I will shade towards the origin like this. This is the third constraint. Now if I take all three constraints together, I am putting these two, first, second, third, all three constraints together, you will see that what sort of region will come. See. So here what you will find, this is first constraint, this is second constraint, this is third constraint, and when all three are drawn, right, I will just try to hold at a point where
right sir.
Now see, this is the common region, this visible region, this again I am moving on the boundary of this common region. So what this is the common visible region or the visible region. I will take the point O, I will take the point A, I will take the point B, I will take the point C, I will take this point D. 5 0, C is I think it is 5 3, B is 4 4, A is 0 6, and this is origin. I will take these points and find the value of the objective function, and whatever value of the objective function, whatever objective function is there, it will be given in the question. I will find value of Z or profit or cost, whatever is given in this question. If it is to maximize the profit, I will find value of Z, and just by comparison we will find out where our profit or our value of Z is maximum. That is the maximum value also we can find, and at whatever point the maximum is attained, from there, like suppose it is 5 3 or 4 4, then x is 5 or y is 3 or x and y both are 4, it all depends upon our objective function. So this is the concept I wanted to explain, that in the visible region all shades will come, and in other regions only green is coming, only blue is coming, or only any two is coming. But here, because there are three constraints, the region which is visible, whose corner points we have to take, is that region where all three shades are coming. So I hope students, you have understood this concept, and in our next session we will be continuing with our linear programming part 2. I hope you have understood. You practice, draw as many constraints as you can, and see how the common region, visible region, and of the optimal value changes as you change the constraints.
Definitely sir, they are going to draw more constraints as you just told them, and I am quite sure, dear learners and viewers, you came to know a lot more about LPP, that is linear programming problems, and we have to wrap up this session here only. But उससे पहले हम राहुल सर आपको बहुत बहुत धन्यवाद करना चाहेंगे. थैंक यू सो वेरी मच. आप स्टूडियो आए और आपने इतने अच्छे तरीके से ये पूरी प्रॉब्लम और ये जो चैप्टर है लीनियर प्रोग्रामिंग पार्ट फर्स्ट हमारे सभी व्यूवर्स तक पहुँचाया. यहाँ पर हम अपने सभी देखने वालों को कहेंगे थैंक यू सो वेरी मच कि आप हमसे थ्रू आउट दिस सेशन बने रहे. आप अपनी बातें हम तक ज़रूर पहुंचाएं, अपना फीडबैक आप हम तक ज़रूर पहुंचाएं. आप हमें मेल कर सकते हैं dth.class12@cit.nic.in पर. और जब तक आप हमें ये प्रोग्राम्स देखते हैं हमें बहुत अच्छा लगता है, अपना फीडबैक भी हमें ज़रूर पहुंचाएं. और अब इस सत्र को, इस सेशन को मैं यहीं पर समाप्त करना चाहूँगी और अपनी पूरी टीम के साथ मैं रेणु भट्ट ले लेती हूँ आप सभी से इजाज़त, अनुमति. आप बने रहें eVidya चैनल्स, NCERT ऑफिशियल यूट्यूब चैनल और PM eVidya चैनल्स पर. नमस्कार.